Okay, good afternoon, everyone. Let's get started. We are in the final session of BICPAMA joint seminar organized by under the support of NTU Singapore and JSPS Japan. So we are in session J, which is actually one of the many sessions on spin-based neuromorphic computing. But in this particular session, we'll be focusing on Scanions and other exploratory topics. We have two speakers, and followed by the so we have two speakers. One is Professor Christos Panagopoulos, So he'll be talking about coupling topological solitons. Then we'll have Professor Suzuki's talk, who will be talking on Scanions. And after the two talks, we'll have the concluding remarks and announcement of the winners from the contributed session. So let's welcome first Professor Christos Panagopoulos, who will be talking on coupling topological solitons in hybrid quantum architectures. Let's welcome Professor Christos. Thank you.
Thank you. I believe.
Yeah, please, you can start sharing now.
So everything is clear.
Yeah, we can see,
Great.
we can hear well.
Thank you. Thank you for the opportunity to discuss our effort to control symmetries in quantum matter. Today, I will show how properties of solitons can be used to develop quantum device architectures. In particular, I will focus on the breakage of spatial inversion and translational symmetries and how these breakages can give rise to topological solitons, which can locally induce new orders with distinctive symmetric, topological, or quantized properties. The topological solitons of interest today are superconducting vortices and magnetic skyrmions, which is, of course, the theme of this conference. Superconducting vortices have been considered for several applications, including cryogenic memory for some time, whereas magnetic skyrmions, as you all well know, hold realistic promise for storing and processing information. For example, multiple skyrmions can aggregate to form storage devices, and the states of such devices can be modulated by an electric current to drive skyrmions in and out of the devices, analogous to biological synapses, for example. But there are still fundamental properties to investigate, such as the wave-particle duality of skyrmions, their interaction with other magnetic textures, and skyrmion lattices as magnonic crystals. Now, importantly for us, the interaction between magnetic skyrmions and other topological excitations could lead to new states of matter. And today, in this talk, I will focus on the effects of spin topology on superconductivity and its relevance to topological quantum computing, which is another dimension that can be considered in the future of skyrmionics. Take, for example, quantum information. It is a promising direction of research, and quantum materials, in fact, play a key role. For instance, we still do not know which qubit technology will prevail. Now, in addition to computing, different quantum materials and architectures may be useful for sensing or network communications. Now, one approach for developing fault-tolerant quantum computers is the concept of topological quantum computing. Here, operations are carried out on anions, which occur in 2 dimensions and can obey non-abelian statistics. This means that if you take anions, as shown on the diagram on the left-hand side, and swap their positions, the final state of the system will depend on the sequence of the individual exchanges, as shown. Now, this path difference is useful to encode information robust against localized perturbations, which is why non-abelian anions are an appealing choice for qubits. Now, as a matter of fact, quasi-particles that obey non-abelian statistics were first observed in materials exhibiting the quantum Hall effect. This occurs in a 2-dimensional electron gas exposed to strong magnetic fields. Unfortunately, however, these materials are impractical for generic quantum computation. Now, another system that may host non-abelian quasi-particles, that is anions, is a 2-dimensional, unconventional P-wave superconductor. It is distinguished from a conventional S-wave superconductor in the way that the spins are aligned in the Cooper pairs that carry the current in the triplet P-wave unconventional superconductor. Now, it is expected that the constituents of an anion, which are known as Majorana zero modes, should appear in this triplet so-called p-wave superconductors, and should appear in the center of vortices, superconducting vortices, that can form in such superconductors. However, these superconductors have proven very difficult to realize in nature. Now, in theory, an S-wave, a conventional superconductor, which is abundant in materials, can be converted to a p-wave triplet superconductor by coupling it with a semiconducting nanowire that has a significant spin-orbit interaction in the presence of an applied magnetic field. Alternatively, however, we can achieve p-wave pairing from combining, as I show you here, Zeeman splitting, spin-orbit coupling, and S-wave superconducting pairing. Here, we have real space, non-collinear magnet onto an S-wave superconductor. A two-dimensional, therefore, vortex configuration would form dispersive Majorana edge states and localized Majorana fermions within the superconducting vortex core of your superconductor. Therefore, building on the concept of a rotating magnetic field, a clever idea for creating a Majorana zero-mode platform for quantum computations would be to couple a superconducting vortex to a magnetic vortex. Now, superconducting vortices appear in certain superconductors upon exposure to a magnetic field. These vortices consist of magnetic field lines, as shown on the diagram on the left-hand side, surrounded by nanometer-sized tornado-like swirls of electric current. Now, magnetic skyrmions, on the other hand, appear in some magnetic materials, as we know. Now, on magnets that have a property known as chiral instability, the spins like to twist relative to their neighbors rather than aligning. And this way, the spins assemble into patterns which are called skyrmions. Now, recently, and this is what I would like to discuss today, we combined magnetic skyrmions and superconducting vortices in a single material for the first time. This is a very exciting and promising, because for many years, theory suggests that combining magnetism and superconductivity in such a way can yield Majorana fermions, as I mentioned earlier. So if a superconductor is brought into proximity with a chiral magnet containing skyrmions, the field from the magnet is expected to change the inter-electron interactions responsible for superconductivity. And this would result in the formation of a so-called topological superconductor. Now, in this superconductor, therefore, the vortices would contain Majorana fermions, which could be useful for a Majorana-based quantum computer. And here, information would be encoded in pairs of Majorana fermions, that is, two superconducting vortices. Now, such pairs would be much more resilient to environmental disturbances than the quantum bits used in existing quantum computers. A major challenge, however, is that superconducting vortices and magnetic skyrmions do not simultaneously appear in a material, let alone interact. So to get around this problem, we developed a hybrid material combining niobium, which is a very well-known S-wave superconductor, with an atomically precise magnetic multilayer made of iridium, iron, cobalt, and platinum. This is a completely new material architecture. It is essentially a stack of magnets and the superconductor. Now, this material, as I will discuss, shows stable superconducting vortices located above elongated chiral spin textures, as well as isolated skyrmions. And it is therefore an ideal geometry to manipulate individual vortices, which is a prerequisite for computational operations. Now, theory suggests that spin textures mediated by Jalozinski-Morilla interaction in a two-dimensional chiral magnet can in fact induce a topological transition to superconducting triplet pairing, that is, an unconventional p-wave superconductor, in a neighboring superconductor which is originally conventional. In fact, a team from Tokyo indicated this back in 2013 using a short wavelength skyrmion lattice. So as you see here in this slide, in their spatially resolved band structure calculations, the team found a gapless state at the edges of their system corresponding to a chiral Majorana edge mode. They also predicted the formation of a localized Majorana mode in a vortex core. More recently, Mascot and collaborators performed calculations using a rather more realistic larger skirmion, as I show at the bottom. They found similar results to Tokyo with a zero bias conductance peak forming at the edge of the ribbon-like sample geometry. They also calculated the induced supercurrent density and found persistent currents circulating around the boundaries of the sample. These are actually consistent with the time reversal symmetry breakage expected for a chiral order parameter. So now we want to take advantage of the Majorana zero mode mobility in a two-dimensional environment while avoiding requirements for strong spin orbit coupling and large magnetic field so that we can have a practical platform for quantum operations. We therefore asked ourselves, can we bring together a localized Majorana zero mode with individual point-like defects in a topological magnet? For example, a magnetic skirmion. The theory says yes, provided that the skirmion teams up with a superconducting vortex. Now, calculations indicate that provided the sum of the skirmion topological charge and the quantized flux vorticity is an even number, then a skirmion vortex pair develops a localized Majorana zero mode in its core. It also develops a delocalized Majorana edge state at the boundary. Now, the spatial evolution of the Majorana probability densities, shown at the bottom left of the slide, in red and green for the core and edge states, respectively. And as you can see from this calculation, the localization is in fact very good. Hence, we asked ourselves if it's possible to develop a magnet superconductor bilayer in which magnetic skirmions and superconducting vortices are coupled into pairs. And recently, we demonstrated exactly that. In fact, even better, we proved that we could build materials in which individual skirmions create their own paired vortices in a neighboring superconductor. So let me discuss now a few details about the development and the characteristics of this quantum hybrid architecture. The key challenge in engineering this hybrid architecture was to match the skirmion and vortex length scales. So our bilayer concept shown here is to deposit a type 2 superconductor on a chiral magnetic multilayer. And for this to work, however, we should clarify first the interactions between the superconducting vortices and the magnetic skirmions in the respective layers of our structure. So firstly, we need to consider the Rush-by-Edelstein exchange coupling. This is a superconducting magnetoelectric effect, essentially. It is actually a spin polarization generating a supercurrent. So here we have a superposition of a supercurrent on vortex currents causing skirmion vortex interaction. And this interaction is controlled by spin orbit coupling and the skirmion exchange field. Now, whether the interaction is attractive or repulsive is determined by the vorticity and the skirmion helicity. So if spin orbit coupling, skirmion exchange field, or the skirmion radius are sufficiently large, the supercurrent allows skirmions to generate vortices. There is also stray field coupling that we need to consider. Here, the interaction is determined by the vorticity relative to the skirmion core polarity. Therefore, an increase in the skirmion radius would favor stronger coupling and therefore a skirmion vortex formation. The stray field coupling, however, would always be present. Furthermore, the Rush-by-Edelstein coupling can be switched off by inserting a non-magnetic spacer between the superconductor and the chiral magnet. So in summary, for exchange coupling, the Skyrmion-induced current must spatially coincide with a superconducting vortex current in order to reduce the free energy of the superconductor. Whereas the stray field coupling, or for stray field coupling, we need to make the Skyrmion radius as large as possible. And therefore, the Skyrmion radius must be between the two fundamental parameters defining a superconductor, namely the superconducting coherence length and the magnetic penetration depth lambda. So here is the design of our magnetic multilayer. This magnetic multilayer works because the key parameters are tunable via the iron and cobalt thicknesses. Also, because these parameters and the multilayer stray field can be modulated by the stack repetition of this architecture. Now, we selected several suitable materials for optimal balance between Skyrmion stability, Skyrmion existence range, and Skyrmion stray field amplitude. And through measurements of the topological Hall effect and magnetic force microscopy, we identified one of the working examples to be a multilayer composed of 10 repeats of iridium, iron, cobalt, platinum with 0.5 nanometer iron and cobalt layers. This multilayer gives us a Skyrmion radius of 47 nanometers. We confirmed the nail texture of our Skyrmions using ferromagnetic resonance, as well as Lorentz transmission electron microscopy. And from FMR, as I show you here, we find that the center of mass of the normalized Skyrmion magnetization rotates counterclockwise in our Skyrmions. Moreover, due to momentum conservation, you see on the right-hand side, the center of mass of the topological charge density remains static. However, its maximum rotates counterclockwise. For the superconducting component of our architecture, we worked with very thin niobium, which is a very well-known and standard superconductor. Those familiar with superconductors realize that the Meissner screening is weakened in thin film superconductors. This implies greater flux penetration. Also, for a film with a thickness less than the magnetic penetration depth, we need to replace the latter by the Pearl length. And furthermore, the superconducting coherence length would be suppressed by defects in the very thin film limit. In other words, in developing the niobium layer, we had to vary the film thickness in order to match the two important superconducting length scales with the Skyrmion size, namely the coherence length and the penetration depth with the Skyrmion radius. After a lot of experimentation, we selected and fabricated niobium films with a thickness of 25 nanometers. Then, by measuring magnetotransport and magnetization, we could apply Ginzburg-Landau analysis to estimate the superconducting coherence length and the Pearl length of our niobium layer. Through that, we find that the coherence length is 10 nanometers and the Pearl length around 200 nanometers. Note, however, that in order to protect these nano-sized samples from oxidation, we capped our heterostructures with a 2 nanometer layer of platinum. Now, platinum has a strong spin-orbit coupling and therefore would modify the properties of our niobium superconductor. Indeed, you can see from our very low temperature scanning tunneling microscopy data, the effective superconducting length is actually higher than the without platinum, and as we estimated before. It is in fact 36 nanometers, but within the range acceptable for the interactions that we are after. Now, this slide depicts the essence of the material, namely the supercurrent and the superfluid density. The superconductor is on the top, and our magnetic multilayer is at the bottom. Now, Skyrmions in the bottom slab, the red slab of the bilayer, can be seen to nucleate antivortices in the top slab, that is inside the superconducting layer. These antivortices, as you can see, coexist with the red vortices, which are parallel to the applied magnetic field. Note the screening currents shown in gray color on the right-hand side. They circulate at a radius which is equivalent to the Skyrmion radius. And their purpose for that is to ensure the stability of the anti-vortices inside the superconductor. We also determined the stray field from the magnetic layer with increasing the applied magnetic field from left to right on this slide. This is shown on the top row of the slide. The lower row shows plots for the corresponding magnetic response of the superconductor. That is, the supercurrent-induced field. The figure at the bottom of the slide shows that the anti-vortex population increases as we go from the Skyrmion nucleation field towards 0. Also, you can see that the anti-vortex density, shown here, is higher when the magnetic and superconducting layers are closer to each other, that is, without a spacer in between. And this is expected since the stray field in these MS bilayers, without the insulator in between, is much higher. Now let us look at the flux dynamics in these bilayer structures. To do this, we made niobium wires which we deposited on a continuous millimeter scale chiral magnetic field. Now we observe, as you can see here, highly resistive flux flow at intermediate fields. With flow instabilities and a remarkable flux flow stability threshold velocity, which is of the order of kilometers per second at low fields. This is remarkable for the fields of fluxonics in superconductors, which indicates that Skyrmions encourage or increase the Skyrmion velocity, the vortex velocity. We also find that superconducting vortices follow a percolative path through the sample, whereas anti-vortices remain above the spin textures, as you can see in the movie, where the magnetization is anti-parallel to the applied magnetic field. Moreover, the Skyrmion and stripe screening currents block the flow of the superconducting vortices. Also, we find that the nucleated vortices and anti-vortices move in opposite directions, perpendicular to the current, and vortex-anti-vortex attraction weakens the vortex screening current repulsion, and therefore we observe a vortex-anti-vortex annihilation at the Skyrmion edge. We can see a new vortex-anti-vortex pair in the movie being created, or in other words, spontaneously nucleated on opposite sides of a Skyrmion, and the presence of anti-vortices facilitating flux flow. Now, how about detection of Rashba-Edelstein coupling? We track the temperature dependence of the field, which we call HSC, where the measured magnetization of the superconducting component of our bilayer first responds to the nucleation of magnetic Skyrmions. Doing so, we find Rashba-Edelstein coupling is enhanced. That is, HSC rises as the effective superconducting coherence length drops in the MS heterostructures. That is, the heterostructures where the superconductor and the chiral magnet are directly in contact. Where on the other hand, the coupling is gradually reduced in the MIS heterostructures, those that we have an insulating spacer separating the superconductor from the magnet. Therefore, as you can see from the graph, as we lower the temperature, HSC falls due to the rise in the lower critical field and weaker thermal fluctuations which suppress the Skyrmion nucleation field. In brief, at low temperature, Rashba-Edelstein coupling and anti-vortex currents interfere constructively, giving rise to enhanced anti-vortex formation. whereas at high temperature, the effective coherence length grows much larger than the Skyrmion radius. So Rush-Beldestein currents and anti-vortices tend to flow in different locations. Hence, the coupling is suppressed. So in summary, our new hybrid material shows stable vortices above elongated chiral spin textures, as well as isolated Skyrmions. Now, this geometry allows you to manipulate individual vortices, which is a prerequisite for computational operations. Now, let us consider the technological potential of our architecture. Assuming the chiral magnet and the superconductor are homogeneous, the Skyrmion vortex pair, and hence the Majorana zero mode, should be intrinsically mobile. This means that we can perform, as I show you on the left, a non-perturbative, non-contact braiding operation without the risk of changing the electron number parity in the system. In other words, as shown schematically on the left-hand side of the slide, simply by coupling the strong stray field of the Skyrmion to a magnetic scanning probe microscope tip and using this tip-to-sample interaction to move the Skyrmion vortex pair around the surface of your material. Now, if we have two Majorana zero modes which we want to fuse for a state readout, chiral magnetic architecture that I discussed today also lends itself very well towards this task. Reducing an external magnetic field will merge two nearby Skyrmions into a single spin stripe, as you see on the bottom right-hand side. This creates an overlap between two Majorana zero modes, which are located inside your vortices. Now, the occupancy of the Majorana fermionic state, which is proportional to the overlap energy, can then be read out by a capacitive or microwave spectroscopy approach. However, before we reach this level of device capability, we have two important tasks to perform. Firstly, we need to ensure that when we assemble the superconducting and magnetic layers in such heterostructures, the magnetic interactions are sufficiently strong to spin polarize the superconductor and cause a topological phase transition in the superconductor. And secondly, if we want to do Majorana braiding by dragging the Skyrmions around with a tip, the magnetic homogeneity of the sample needs to be much better than what we have achieved to date using magnetron spattered fields. Now, meanwhile, however, we can of course make progress through a non-local experiment to infer the presence and the number parity of Majorana zero modes in a topological superconducting island device. So, for example, the simultaneous tunneling into a Majorana edge mode at two separate locations should reveal noise currents whose cross-correlation is controlled by the number of vortices penetrating the spin texture. With this, I would like to end my talk by thanking my group in Singapore for developing this hybrid architecture and demonstrating the Skyrmion vortex coupling, but also my colleagues at Technion in Israel, Geneva in Switzerland, and Antwerp in Belgium for the pleasant collaboration leading to this work, and for your patience to listen to the work. Thank you.
Thank you, Professor Christos, for the very interesting talk. Let's open the floor for question. Any questions from the audience? Maybe I want to ask a general question. Do you find any difference in the TC of niobium when you sputter thin film?
It varies a lot depending on the quality of the sputtering you do. So indeed, our TC is quite high for a thin film of such a thickness of 20 nanometers or not. But it was not a straightforward situation. So in brief, it takes a little bit of effort to achieve homogeneity and quality of a niobium film using sputtering, especially when you want to go so thin.
So does the grain size or something affect?
It does affect.
Okay.
So yes, it does take some effort.
Okay, thank you. Professor Rawat?
Yeah. Hi, Christos. Thanks
Hello.
for talk and many things. Yeah. I just wanted to ask, so One thing I wanted to understand, the movie that you were showing where you have a vortices and anti-vortices moving in the opposite direction and then they annihilate. These vortices or anti-vortices that are developed, are they also locked to the skyrmion and the underneath the chiral magnetic layer?
Yeah.
So at the time when these two guys annihilate on the top layer, what happens to the skyrmions? There must be two skyrmions also colliding downstairs or something like that. Do they also annihilate or?
So for instance, in this case, as you can see in the movie, the vortices, or in the schematic up here, basically. First, the situation goes like this. The vortices and the anti-vortices move in opposite directions to start with. So the skyrmion would nucleate an anti-vortex first because of the polarity. Then the vortex-anti-vortex annihilation will take place at the skyrmion edge.
Oh, okay.
So then, after that, on step number 3, what happens in practice, in reality, is that you get a new vortex-anti-vortex pair spontaneously nucleated on opposite side of a skyrmion.
All right. So skyrmion itself remains intact all the time.
That's right. In this case. In this case, if you want to move
sorry, another question I wanted to ask is that, so skyrmion over here itself is stationary. You are not making it move, or that one?
We don't want to make it move here.
Okay.
That was not the purpose.
All right. No, I was wondering that suppose if skyrmions are also moving and if they suffer the so-called Magnus effect.
No.
What happens to the vortices at the top also?
So at this stage, which is the first stage of this project study, let's say, our effort was to show that the skyrmions can induce anti-vortices, number one. Number two, to indicate or to show that the vortex flow in the superconductor is highly affected by the presence of skyrmions or spin textures in the chiral magnet, stripes, for instance, etc. And B, to show that the skyrmions and the vortices, not only, they actually couple, and therefore you can move them around by moving the skyrmion.
Skyrmion, yeah.
That's right. So the next step is actually to be able to do this operation that I mentioned, which requires higher quality samples.
All right, thank you.
Okay, Professor Suzuki, please ask your question. Please unmute your mic.
Thank you. My question is about the dissipation in the magnetic film. So you told about inhomogeneity of the magnetic film, but also the magnetic film has the dissipation inside. So for the Majorana quantum computing, I am afraid about the problem of those dissipation.
The magnetic field inhomogeneity that is mostly concerned here is the inhomogeneity due to the inhomogeneous quality of the magnetic multilayer and therefore the magnetic interactions. So if you assume, which an experimentalist should practice actually, that you have grown this with a high level molecular beam epitaxy, you should be able to move to the level of materials used for quantum Hall effects. This is actually where we would like to move to. That is, take this to the high crystallinity where magnetic inhomogeneity in the material is negligible. Then we should be able to have the quality of Majorana braiding that we need.
Oh, my question is that dissipation in the magnetic material.
Now, so the dissipation in the presence of a magnetic field, you mean?
Yeah.
Okay, so this is a next step which we have already done. In fact, we can stabilize magnetic vortices and superconducting vortices in nanodots in the absence of a magnetic field. That is, we can have a nanodot where a magnetic skyrmion can be nucleated in zero magnetic field. And that field, and then the magnetic skyrmion's stray field should be sufficient to create a superconducting vortex-anti-vortex above in the absence of an applied magnetic field.
Okay. Yeah, thank you.
And this is doable. This is actually possible. It's been done. We've done it. For the skyrmion.
Thank you.
Thank you.
Are there any other questions? Okay, if not, let's thank Professor Christos. Thank you very much.
Thank you.
Let's move on to the next talk. Next talk is by Professor Suzuki. So he'll be talking about diffusion of Scanion and its application to zero energy calculation. Let's welcome Professor Suzuki.
Hello. Oh, just a moment. Okay. Can you see my screen?
Yes.
Yes. Hello, my name is Yoshishige Suzuki of Osaka University. First of all, I would like to say thank you to the organizers who gave me this opportunity to talk my recent study in this interesting conference. My subject of this talk is diffusion of Scanion and its application to the Brannian computing. This work is based on our collaboration between Osaka University, Alba Corporation, AIST Tsukuba, Mie University, and SciNet, Suita, Japan. Just a moment, I prepare a pointer. Okay. So here I start with these pictures that I took from literatures. As it was already mentioned in the previous talks, the probabilistic phenomena are useful for the advanced computing. The probabilistic computing includes several methods. The first one is literally the probabilistic computing. The probabilistic numbers replace complex calculation tasks by simpler operation. Here it shows that this probabilistic number 6/8 and 4/8. If we do the AND calculation for those bits, we get 3/8. That is multiplication. And this was done only by using AND gates. That is much easier and faster than multiplication circuit. To implement it in hardware, one may use magnetic Scanion system, for example. Therefore, certain groups are working on this direction. The second method is so-called p-bit. There is a system with interacting probabilistic bits. The system can be regarded as a Bayesian network and may solve the minimization problem efficiently. The p-bit also may compose the dynamic Kalman filter. The p-bit is a classical version of the qubit. The quantum annealing machine uses probabilistic nature of the wave function. Therefore, it is also a probabilistic computer. The final one is a Brannian computing. This method uses fluctuation of the thermal equilibrium to facilitate the calculation. In this talk, I will talk about application of the magnetic Scanion to those two types of computations. Those are p-bit and Brannian computing. Let me explain a little bit more about Brannian computing. The Brannian computing is based on an idea of reversible calculation. If the information processing is irreversible, it consumes energy. Landauer shows that erasure of a single bit needs energy emission of kBT log 2. However, if the calculation process is reversible, it is not necessary to consume energy for the calculation. There are two types of reversible computing, either ballistic computing or Brannian computing. Ballistic computing uses mechanical system without scattering or friction. Quantum computing is an example. It is a unitary transformation and reversible. On the other hand, Brannian computing uses thermodynamically reversible system. For this case, one may use system with frictions. Brannian computing uses thermal fluctuation to explore the correct answer. Therefore, it does not use energy for calculation. Here, the picture shows a famous proposal that was given by Bennett in 1982. It is the RNA Turing machine. To assure one-way progress of the calculation process, one may use the small energy gradient. Such a machine is used in our human body. Here, I show you two examples of the utilization of the Brannian motion in the human body. The replication process of the DNA can be done using 20 to 100 kBt per nucleotide molecule. Host chain searches for the correct nucleotide by use of Brannian motion. The mechanism of the mask motion is also very famous. Myosin molecules move to the objective position by using thermal fluctuation. The myosin fixed mechanism uses only 3.3 kBt for a cycle. As it is shown here, by use of Brannian motion, ultra-low power processes are feasible. Next, I will explain about our numerical simulation of the Brannian circuit. The work was done by Dr. Utsumi of Mie University. Here, it is an example of Brannian circuit. It is a half-adder that is proposed by Dr. Pepper of the NICT. Black dots are information tokens. We put tokens at, We put tokens at the corresponding input wires. Then both tokens show Brannian motion and search each other. Three square boxes are conservative join, which correlate two tokens. Only when two tokens arrive at the C-join at the same timing, the token goes through. As a result, we find, here you can see, okay. As a result, we find those tokens in the correct answer wires at the end. Yeah, this is a bit complicated circuit. It is a Brannian 2-bit adder, which is composed of 4 half-adders. Utsumi and Ito analyzed the calculation time distribution and the energy consumption of the circuit under the consideration of thermodynamic uncertainty relation. Since the circuit is based on the thermal fluctuation, the calculation time is scattered like this. Here's the distribution of the calculation time for 2 cases. The left-hand side corresponds to an irreversible process. And the right-hand side shows the distribution for the reversible process. The reversible process uses longer time for the calculation. Here this is 100 and here this is 200. So it takes about 2 times longer time for the calculation. But the reversible process uses the longer time for the calculation. However, the emission of heat to the environment is 0. Okay? The reversible Brannian computing realizes the calculation with 0 energy consumption within a finite calculation time. In addition, since internal information transfer is done by Brannian motion, there is no energy need for the communication inside. Only the input and output processes to the circuit requires energy. The Brannian computing can be realized by using any objects that shows thermal fluctuations. For example, the single electron transistor is a good candidate. In our experiment, we have tried to use magnetic Scanions. We selected Scanions because of several advantages that I will explain later. As you know, the magnetic Scanion is a particle-like magnetic domain. Okay? And the size of the Scanion can be from nanometer to the several micrometer. For the Scanion that appears in the ferromatic film, we use perpendicularly magnetized film with interfacial Jaruzelski-Morier interaction. There are nail type. Pardon? Is it okay to continue?
Yeah, please continue. I think the audience.
Yeah. For the Scanion that appears in the ferromatic film, we use perpendicularly magnetized film with interfacial Jaruzelski-Morier interaction. There are nail type and block type Scanions, but the Scanion made by interfacial DMI is thought to be nail type. That is shown in this picture. If the mapping to the sphere covers sphere once, the Scanion number is 1. Okay. Since the Scanion can be driven by small current, those are good candidates as an information carrier in three-dimensional racetrack memory. Yeah. If we use them in the Brannian circuit, we can expect room temperature operation that is difficult for the single electron transistors. The Scanion Brannian computer will realize zero energy calibration and zero energy communication. So next, I will explain several important properties of the magnetic Scanion. The Scanion shows Brannian motion at ambient temperature. Usually, Brannian motion occurs for the particle sintered in a liquid, okay? Like flour powder particle. However, the Scanion exists in the all solid-state system and shows Brannian motion. This is a fantastic future for the solid-state electronics. Scanion can be controlled by electric current and voltage. These pictures shows the example of the voltage creation and annihilation of the Scanions. So we can annihilate and create Scanion by voltage. Scanions have a very small mass. It makes ultra-fast control possible. Scanion is a chiral object. It may offer new functionalities that I'll mention later. There's a significant Scanion-Scanion interaction. It is essential to implement direct information exchange and information feedback into the Scanion system. Here's the purpose of my research. We developed a Brannian computing system by using magnetic Scanions. For this purpose, we analyze the Brannian motion of the Scanions. We try to control Scanions by current, voltage, and magnetic field. Then we develop primitive devices that construct the Brannian computer. Analysis of the Brannian motion was done mainly by these students and staff in the Osaka University. The film was sputter deposited on the silicon wafer, having SiO2 surface. The deposited layer structure is shown here. The scanion is created in the cobalt iron boron film. Tantalum to cobalt iron boron interface provides interfacial DMI. And the cobalt iron boron to MJO interface provides surface perpendicular magnetic anisotropy. This inserted ultra-thin tantalum layer is to adjust the strength of DMI to the anisotropy. Usually, cobalt iron boron film in the magnetic tunnel junction is annealed to obtain high tunnel magnetic resistance ratio, but we found, however, this crystallization process increases the pinning site of the scanion and reduces diffusion constant. Therefore, we made a film without annealing. Here, you can see the micro optical image of the film. Fine vibrating particles are scanions. The size of the scanion is about 1 micrometer. From this observation, we digitized the position of the scanion and calculated the diffusion constant. This is an Arrhenius plot of the diffusion constant. The x-axis is the inverse of temperature, and the y-axis is the diffusion constant. The film without annealing here shows the higher diffusion constant and the smaller activation energy, the slope, compared to the previous experiment. For the next, we confined the scanion in the one-dimensional channel. Here. The channels is realized by soft potential modulation by the post-deposition of the ultra-thin SiO2 layer. So you can see here those parts where the SiO2 is deposited, the scanion does not exist. Yeah, you can. Okay, so the right-hand side graph shows the channel width dependence of the diffusion constant. This is a plot for the two-dimensional film. These red dots are the diffusion constant for the diffusion along the channel direction. The diffusion constant along the channel increases in the thinner channels. This property can be understood as a consequence of the gyro motion of the scanion. Since scanion is in spiral particles, it does not move along the force direction and tend to move with angle. It can be regarded as a scanion Hall effect or gyro motion. Because of the gyro motion, diffusion is suppressed in the two-dimensional film. If we put it in the one-dimensional channel, the gyro motion is suppressed, and we may see such increase in the diffusion constant. Therefore, this is the proof that the gyro motion is important in the diffusion in the scanion. The diffusion constant discussed in the previous slide were given by plotting the mean square displacement, displacement as a function of the elapsed time. And this slope provides the diffusion constant. But for the case of the chiral motion, we cannot obtain the information from the, for example, XY observation. So we try to observe the velocity position correlation function. And it also provides the diffusion constant for the diagonal part. This is a usual normal diffusion constant, but also we find that there is the off-diagonal element. This offline element does not provide the diffusion, actually, because the off-diagonal motion is the divergence-less. So this flow does not appear in the diffusion equation. But this flow, the rotational flow, is non-zero by the observation of our experiment. Since this diffusion constant does not appear in the diffusion equation, we call this is hidden diffusion. And the existence of this hidden diffusion means that there is non-zero angular momentum of the Scanion in its thermal motion. Okay, so this is LLG micromagnetic simulation result. The Scanion is in the harmonic potential, and only by the thermal vibration, the Scanion shows the rotational motion. Oh, why it does not move again? Okay, so it shows rotational motion spontaneously. Such a strange property of the Scanion may have some application that I will introduce later. Now I switch to the discussion to the result about electronic control of the Scanions. Here, in this picture, current is flowing vertically, but the Scanion tend to turn left-hand side. This is a Scanion Hall effect. The result confirms that we are really observing Scanions. This center graph shows the external voltage dependence of the diffusion constant. The electric field perpendicular to the film may change magnetic anisotropy, exchange energy, and DMI. As a consequence, the diffusion constant can be controlled electrically. Since voltage application in the high impedance circuit consumes only very low energy, the phenomena provides low energy control method of the Brannian circuit. The left-hand side photograph shows magnetic field control of the Scanion. By installing an additional current wire on the film, we can control Scanion potential. In the zero current, the Scanion distributes uniformly, but under the current, we can evacuate the Scanion from one side. Of course, this is a very energy-consuming method, but for the first demonstration, we use this method. Next, I will show you some trial to make primitive devices. The Brannian circuit can be composed of these primitive devices: hub, conservative join, and ratchet. The hub is a kind of T-crossing. The Scanion can select either go to the right-hand side or left-hand side. I have already explained the conservative join. And ratchet is a rectifier of the Scanion flow. Okay. At the beginning of our study, we have constructed hubs by cutting the filmatic film into the wire like this. Okay. For this case, however, we found that Scanions are trapped at the corner and cannot move freely. Okay. Therefore, we have developed the method to form channels without cutting filmatic film. The method was already explained in this talk. In this new hub, the Scanion moves freely around this circuit. Here, to check the possible effect of the hidden diffusion, we measure the transmission probabilities in the hub circuit. In this result, we did not see any significant difference in the transmission between the right turn and the left turn, but by simulation, we could see the certain difference between the chirality. So the Scanion hub can act as a circulator, we think. This is a movie about the C-join function. The two particles are coming from left-hand side, and one Scanion goes under the current wire, and another goes under the wire also, and then the lower Scanion appears, and the second one appears in the right-hand side. Okay? This control is made by observing Scanion by optical microscope, and the student changes the current by hand. This human feedback enables C-join function using, of course, huge energy. On the right-hand side, now you may see the Scanion in a rectangular box. The left-hand side of the box corresponds to the 0, and the right-hand side 1. Why it does not move? Sorry. It should move also, but it doesn't work. Okay, the left-hand side of the box, okay, and under the 0 current, the Scanion fluctuates between 0 and 1. By the current in this additional wire, we apply an asymmetrical magnetic field and control probability distribution. Okay, this wire. It is a function of as a pivot. Those devices are functioning by using huge energy. To realize ultra-low energy devices, we need a built-in type feedback mechanism that I will show you in the next slide. Here is the final part of my talk. Now we prepare a square box, and the two Scanions are confined in the box. Since the Scanions show repulsive force, two Scanions in a box prefer to stay at the corner in the diagonal position. This positioning corresponds to 0 and 1. Then, because of the interaction between the boxes, the Scanions in the different boxes correlate each other. Okay? There are correlation between two boxes. This is a kind of information transfer, and we can use this mechanism for the information feedback also. Actually, this kind of design was proposed for the single electron transistor at the end of the 20th century. The system was called quantum cellular automata. Here is a design for the logic gate. Single electron transistors did this task at very low temperatures. The Scanion Brannian computer may do it at room temperature in principle. Since this design is the same as a pivot, it can do what the pivot does without using energy in principle. However, a large-scale calculation will require exponential time, so we will need to include latchet and C-join place to place to avoid explosion of the calculation time. This is the final slide. This slide shows an example of the device based on the Scanion cellular automata. If we place three input around one box, output will be determined by majority of the input. Therefore, the device works as a majority gate. Here is an experimental realization of the device. Okay. We put three fixed bits around the box. By this configuration, the device should show an OR function, OR gate function for the 1 and 1 input. The result is following. Okay. The probability to show the 1 is about 80%, as that is expected from the design. The interesting point of such a device is that we may construct reversible logic, which may do reverse calculation, such as factorization of the rational numbers. Okay. Here is the conclusion. The Scanion shows hidden diffusion. It is a chiral diffusion of the Scanion. The primitive for the Brannian computer and the pivot has been developed. To realize real ultra-low energy computing system, built-in feedback is essential. Thank you for your listening. Thank you.
Thank you, Professor Suzuki. Now the talk is open for discussion.
Let me ask questions, Professor Suzuki. Very much interested in the extremely low low power device,
Yeah.
like a brain.
Mm-hmm.
But looking at the p-bit picture that you show in the last slides, the motions are more like probabilistic. It's Brownian motions. So how we can define the error like a digital bit calculation operation? We live in a digital system right now, so we easily calculate the bit error rate or something like that. In case of p-bit here, how do you define the idea of error, and how, if it's there, what could be the error correction scheme potentially embedded in the system?
Okay, thank you very much for interesting question. So for this case, this is the OR circuit, and if we use usual CMOS device for the OR, certainly we should have 100% one output. Output should be 1, but for this circuit, we got only 0.77. So this contains a big error. But this has the potential, as I told you, that it can do the reverse computing. That's a very important point. And if you want to have the correct answer, you need to do the annealing. I mean that now it's in the high temperature, so you should lower temperature, then the system will be fixed to the correct answer if you are lucky. Okay, so but unfortunately, it's the same for the quantum computing. For such annealing machine, we are not very sure about result. If result is really perfectly correct or not. But this machine is very good for the case of such task like factorization. If you get result, you can check it easily if it is correct or not.
I see.
So then to find such possibility, this is a very good machine.
So we need to change the our scale of the error rate.
Yeah, and also
it's totally different things.
Yeah, we need to select the tasks.
Okay.
Yeah.
Thank you very much.
Thank you. Any other questions?
Okay, may I ask one question?
Yeah, please.
Okay. Prof. Suzuki, when you were showing your hub configuration, for the first case where you patterned the wires, there were no Fermion motion. May you please comment what was the reason for that?
Pardon? Oh, you are talking about this?
Slide number 23.
22, sorry, 22.
20. Yeah, 23, yes.
23, okay.
Yes, so here,
Mm-hmm.
in this case, there were no proper Fermion motion observed, or Fermions are trapped.
Because Scanion is very, very sensitive to the external field. Actually, external field gradient.
Mm-hmm.
And if you cut magnetic wire, even if this film is very thin, like 1.3 nanometer for this case, even so there is stray field from the edge. If this stray field is not uniform, then Scanion can be trapped by this field gradient. That's the case of this circuit. But if you don't cut the magnetic film, then there's no such field gradient, and Scanion can move freely. That's our result. Is it the answer to you?
Yeah, okay. So one more quick follow-up question. So for the material stack structure, right, I noticed there is a very thin 0.22 nanometer tantalum layer on the top of cobalt iron boron.
Yeah.
What was the reason for that again?
Yeah, it's good question. And I also want to ask you to the same, because we don't know very well about the mechanism. We imagine that maybe there is strain, and this additional strain provides the change in very small change in the anisotropy.
Okay.
That's our guess.
Okay, thank you.
Thank you.
Ramu, you have a question?
Yeah, I have a question. Prof, it was a nice talk, Suzuki. So I have a question in the slide 24, the next slide. So in this case, what is the direction of the current that are applied? Is it like the branch structure? What is the direction of this current?
No, there's no current. This is only Brannian motion. But Brannian motion is not really symmetric.
So how can you control the motion then in this case, like if it wants to go upper branch or lower branch?
No, we don't control.
Okay.
Yeah, and so just a moment. For example, but we don't control, but if the two Scanions find each other, for example, if we put here C-join, we can correlate them. Okay? And that's calculation.
Okay, Shreya.
Yes, hello, Professor. Thank you for your nice talk. I also had a question from slide 24. Actually, I was wondering that you have mentioned about LLG and Brownian motion here, but frankly speaking, I have just started studying about Fermion, but the basics that I have gone through says that it also follows the motion that can be calculated from the Thiele equation, because there is also so, but why you are carrying on the LLG simulation? Like, is there any relation through how we can calculate the position and the velocity of the Fermion?
Okay, nice question. So we are also trying to do this calculation by using segregation. And the difference between them is that, for example, the wire thickness is very important to have this case. For the very thick wire, there's no circular function for this circuit. But if the wire thickness is very correct, then we have the different possibility to turn right and left. So to find it, we use LLG. But I think that if we can make correct potential from the wall, then the segregation is also provides the same result. But not yet we have succeed in this type of calculation. Please do it.
Yeah, okay, sure. Thank you so much.
Any other question? Maybe I ask one question in the same slide.
Yeah.
When we have Scanion Hall effect, if the Scanion goes to one edge, it collapses. So does it happen in the case of Brownian motion also? Let's say if it goes to the edge, will it collapse?
Okay, so if you give the strong force to the Scanion, for example, if you pass through the large current, then Scanion has a force towards a wall, and then you may see the collapse of the Scanion. But for the some vibration is a little bit different, and often, unfortunately, Scanion evaporate by the effect of the temperature, even if it is not at the edge. So we need to avoid that for the calculation. That is important task also.
What is the DMI in your film? Yeah, you have used tantalum only.
We have not measured, but there is several groups. They are using the same film structure, and they measure it at 0.3 millijoule per square meter.
Okay. Thank you.
Professor Krai's group.
Okay. Any other question from the floor? If not, let's thank Professor Suzuki for showing us an interesting concept. Thank you very much. Thank you.
Thank you.
Okay, so with this, we are moving to the conclusion part of the seminar, 1 week long seminar. So first of all, I would like to thank Professor Tanaka, because when I approached him 2 years ago that we will do this seminar, he very keenly showed interest, and then onwards we have been working together. So I first like to thank Professor Tanaka. Then secondly, both of us, Professor Tanaka and me, thank JSPS and NTU Singapore for the support of this conference. Then also I'd like to thank Saprit for helping me this 1 week with the organization of the seminar over Zoom, and he also helped to prepare the certificates. Then I also wish to thank one Twitter group called Physics Front. They helped to advertise this conference in the social media, and thereby we got a lot of participation. Then I also, we both of us, the chairs, would like to thank all the session chairs listed here. So they help to run the seminar smoothly, and we also would like to thank all the invited speakers who spend their time to prepare slides and do the presentation. Then maybe I want to show some statistics. So this symposium was advertised over email, Facebook, and Twitter, and we had registration of about 183 participation registrants. The majority came from India, so there were 79 registrants, and from Japan and Singapore we have about 50 plus registrants. And there are also participants from neighboring countries like Philippines, Thailand, and so on. And we also had a few registrants from many different countries. So this is basically the demographic of the attendees. But every day we were organizing both in Zoom and YouTube. So the Zoom participation is typically 20 or so, and YouTube around 10 people attend. So roughly every session has like 30 people. Yeah, not everyone attends every session. So that has been the way it was running. Then I also wanted to show a brief history of how this whole thing started. Basically, JSPS and
sorry, Prof. Are you sharing screen?
Yeah, is it not moving?
No, we are not getting anything. Actually, I am not getting anything.
Okay. How about others?
Oh, we don't see any slides.
We don't see anything.
No, the screen is not shared, I think.
Okay, let me see what the problem. Okay, now you can see the screen, right?
Yeah.
Okay. Yeah. Thank you. Thank you for feeding back. Basically, the previous two slides I showed the names of the speakers and the invited speaker, the session chairs, and so on. So probably we didn't hear. So JSPS and some organizations like NTU and NUS in Singapore, they can organize joint seminars, or they can carry out the research projects. The money may not be much, but the money they give for project is good enough for improving the interaction. So people from Singapore can travel to Japan, and people from Japan can travel to Singapore, and so on. So similarly, we also are encouraged to organize a joint seminar. So initially, Professor Tanaka and we wrote the proposal in July. At that time itself, we identified the speakers, contacted them. Then we wrote the proposal and we got the project awarded in January 2020. And we were planning to organize this conference in December 2020. But soon after we got the project award, the COVID-19 came. Then we kept delaying the seminar, thinking that we can probably organize an in-person conference. But unfortunately, COVID-19 has been mutating and so on. So we have now Omicron version. So this couldn't happen. So that's why we have to organize the online event, virtual event. So that is the history. Then we also were planning to organize contributor talks in a special session from 5 to 6 p.m. if there are many responses. However, we got only 9 submissions, so we could manage all the talks within the 3 to 5 p.m. slot. So, basically, I would think all who volunteered to submit a paper as a winner. But today I'll announce the winner in the next few slides. So the judge for the deciding person for this winner is Professor Tanaka, who has no conflict of interest. Okay, so as I mentioned, all are winners. So we don't give the participation certificate. We give all merit winner certificate. Then we also have 2 silver winners and 2 gold winners. Okay, so the first merit presentation goes to Jampeng. Then we have Neha Garg from IIT Delhi. She also get the merit presentation. Then Sonal Shreya from Europe. Then we have Sri Lakshmi from NTU Singapore. She presented the optoelectronic transistor talk. Then we also have Timothy Ng, who talked about the photo detectors. So these are the merit winners. Then now I proceed to announce the silver winners. So Mona Lisa from IAC India, she gets the one of the best presentation award, silver. Okay, then Ma William from NTU Singapore gets the best presentation, silver award. Okay, so now we have 2 gold winners. So one is the Devesh Kumar from NTU Singapore. He talked about the novel engineering of spin-torque layers. Then we have one winner from Japan, the Kyujin Shin. He talked about the CMOS invertible logic. So let's applaud all the winners and congratulations to the winners. And before I pass the mic to Professor Tanaka, I also would like to give an advertisement for the symposium that we organize in IEEE Magnetic Society every year. So we have one coming up in the next 1 week later. So if you have any questions regarding the IEEE Magnetic Symposium, please contact Varun Chaudhary at this email. So let me pass the mic to Professor Tanaka.
Thank you, Prem. Thank you, everybody, to joining this BICPAMA joint seminar. So at the beginning, we planned to bring all the Japanese invited speakers to NTU Singapore, but due to the COVID-19, we had to give up. But instead, we postponed and hold this remote seminar style. But thanks to this system, we have more than 180 attendees, registered attendees from worldwide. That was a good point of this. So we remember brain-inspired computing. The basics of the neurons and synapses are fire together, wire together. So that's a keyword. So all of us fire together in a 5-day seminar. Now we are connected. We are wired. So that's a great power for us to go beyond the next step. So hopefully we will see you in the future conference and get connected more. Thank you very much. Thank you very much for attending this seminar.
Okay, thank you all. Happy holidays and happy 2022. See you somewhere in the future. Yeah, thank you.
Thank you very much.
Thank you. Bye-bye.
Thank you.